Welcome back to part 3 of this fatigue analysis of cylindrical rod subject to reverse bending loading. In this part, we are going to discuss the analytical solution that we can then compare with the value of the fatigue life that we have determined from this shaft. And in the last part, I showed you that the minimum fatigue life of this shaft is 53,318. And then based on the area of interest that we have defined, we saw that the minimum number of cycles in that area of interest is 242,663 three cycles. So basically, that's on this, which you can also read directly from this plot in the region of the interest. So it's around 267,000 cycles that you're seeing here, or actually so roughly around that. But in terms of the actual number, we have got the summary of that region over here. So and it is 242,000 cycles approximately. So this is the number that we will be comparing with our hand calculations. And to compare against the hand calculations, we need to carry out the analysis using the beam equation. So basically, what we have over here is we'll use first of all the beam stress formula to calculate the static stress because of this 1500 Newton load. And the beam stress for familiar beam stress formula, mc over I, we will be using, in which m is the moment because of this force, and c is the distance of maximum distance from the neutral axis, which is d by 2, or the radius of this shaft, and I is the moment of inertia of this shaft. So substituting the numbers, Fy into L minus x into d by 2 divided by pi d4 over 4. So once we substitute all of these numbers, the stress from the in the due to the bending of this cantilevered beam comes out to be 1500 multiplied by 0.25 minus 0.5, which is the location of interest. Keep this in mind. If you change this location of interest, you will have to change then this number to get the particular value of the stress. And then multiplied by the radius of the shaft divided by the Bohr moment of inertia, and then converting it to megapascal, you get the final answer as 195.6 megapascals. So that's the value of stress in the shaft due to the X stress in the shaft due to this load. Now, we can also calculate the value of the shear stress in this shaft, which will be given as VQ over IT. Again, the formula that you have considered in the class, but because this is a cantilevered beam, and the shaft length is significant. Okay, so this is a significantly long shaft as compared to the diameter. So we are assuming that for this particular shaft, the value of the shear stress is zero. This assumption is actually is more strictly valid on the outer periphery of the shaft where we are considering the maximum stress. Now keep this in mind that the shear stresses in the beam based on the formula, the VQ over IT formula that we have covered in strength of materials, is maximum at the center of the shaft. Okay, and it's in the based on that formula, the outside shear stress is always zero. So this, regardless of the geometric parameters of the shaft, that formula will be true. Will give you a shear stress of zero at the outermost periphery. So now from using these two values and of the shear stress and the sigma y equal to 0, we can now calculate the principal stress from the principal stress formula. Again, this is the direct formula that we covered in strength of materials, and from based on this formula, you can see that the principal stress and the von Mises stress in this case will be equal to sigma x. Now, keep this in mind that in the once you calculate this value of the von Mises stress, you can now use this to calculate the alternating stress in the material. Okay. So because this is a fully reversed cycle of the load, therefore the maximum and the minimum values of the stress will be same. Therefore, but just with the opposite sign. Okay. So the alternating stress and the mid-range normalized stresses can be calculated as sigma max minus sigma min over 2, which means it is this value which we got over here, 195.6 minus, and then minus, which is a negative value, divided by 2, which is will give us 195.6 megapascal as the alternating stress. The mean stress, in because it's a fully reversed cycle, should be 0, which we can see here as sigma max plus sigma min over 2 is equal to 0. So that's what we will get. So this, because we are using stress life approach, and this is, we are expecting this to be a high cycle fatigue case, we should be well away from the yield stress. So this is what we can check. So basically, the alternating component and the mean component, when you add them together, should be less than yield strength. In this case, this is case because 195.6 plus 0 is less than the yield strength of the um, of the material that we have used. So the material's yield strength in this case was 351.571. So the material's yield strength, if you are unsure, you're thinking, where did I get this value? So actually, this value is coming from here, from SolidWorks, basically for the material that we use. So it was 351.57. Now, with that number being compared, meaning that we are well below the yield stress within the material, we can proceed with the analysis. So now what we need to do is to calculate the number of cycles to failure. We have to calculate the value of A and B, basically. So the calculation of the constants A and B. Now, these constants will be then used in the equation, which is over here. That is, n is sigma dash, which is the normalized stress divided by the value of A constant raised to power 1 over B, and this will give us the number of cycles. So in this case, the constant A is given by F multiplied by the ultimate strength. So basically, this is telling you the start of the high cycle fatigue range. So basically, the ultimate strength multiplied by the 0 0.9 in our case. So that will give you the strength, which is at 1000 cycles, okay, divided by the endurance limit strength. Endurance limit strength in our case is the endurance limit modification factor K multiplied by 0.5 into SUT, which is the ultimate tensile strength. So just to make sure that what I'm explaining also makes sense in terms of the formulas that we will be covering in the tutorial section as well. So you can see in this graph, so we took the 10 to power 3 cycle strength as zero point 0.9 SU for the bending case, which is this top line. And then the endurance limit was taken as zero point 0.5 SU. And of course, then this needs to be multiplied by the factor K over here, right? Which is the correction factor, which will be a multiplication of CL, CG, CS, CT, and CR. Then you multiply all of them, which we are calling all of these as accumulative as K in our case. Okay, and that's what we use over here. And in this case, the K value was already provided to you in the simulation, which we used as 0.7854. So we have to use the same constant K over here. So with that, the value of the constant A comes out to be 867.3 megapascals, and the value of the constant B will be minus 1 by 3 log base 10 into F into SUT divided by the endurance limit, basically SE, which is given as K into 0.5 SUT. So once you have this number, which is 0.1201, you can now read the number of cycles simply as the alternating value of the stress, which is 195.6, divided by A, which is 867.3, raised to power 1 over point minus 1201, and this comes out to be 244,389. Now this number actually is pretty close to the value which we already saw from our probe tool by looking at this edge, and this number over here we saw was 242,663.297. That was the minimum value on this edge. So basically we can also now calculate the percentage difference, and we see that there is only a little percentage difference between this. So with that, our analytical solution is completed. So when you do the assignment, I expect you to do a similar procedure as well, but you will need to also account for some of the differences. Like there, you will have a mean stress as well. So make sure you read a little bit more, and I want you to consult some external references so that you can then find the correct equations for that case, and then do the verification of your assignment problem as well. So thank you very much. I hope you will be able to understand this, but if you have any questions, make sure you can ask me in the lab. Thank you.